Impulse is the... Just kidding, no raps today. Today's lesson's on impulse and how it relates to momentum. It's a very important subject. We'll talk about the purpose of airbags in cars. I'll give you some examples of impulse and how it relates to changes in momentum. But first, let's do a little math, because math is awesome and math is fun, and how it relates to science. So Newton's second law. Everybody recall Newton's second law? Tell me what it is right now, off the top of your head. Newton's second law. Yeah, force is equal to mass times acceleration, or net force is equal to mass times acceleration. So we'll write that on the board here. Force is equal to mass times acceleration. So what is acceleration then? That one goes back a ways to like the first week we started doing physics, or maybe the second week. What is acceleration? It's change in velocity over time. So algebraic substitution, can we substitute in change in velocity over time for acceleration? Well, yes, that's legal. We could do that. So force is equal to mass times change in velocity over time, if that's what acceleration is, change in velocity over time. Well, how do you find change in velocity? It's always final minus initial, so final velocity minus initial velocity. So let me change that out. So final velocity minus initial velocity. So mass times acceleration. Well, let me distribute my m. Let me multiply through by m. And so let's see what we get. Force is equal to mass times final velocity, m times final velocity, minus m times initial velocity over time. Well, does that right there look familiar? It should, if you paid attention to yesterday's lesson and you did the problems. Mass times velocity should look familiar. Well, what is mass times velocity? That's right, that's momentum. So this would be final momentum minus initial momentum. Well, what is final minus initial? Once again, change in. So this would be final momentum minus initial momentum, or another way of stating that is force is change in momentum over time. So basically, a net force acting on an object, if it's an unbalanced force, causes a change in momentum over time. So we derived this from the acceleration formula and Newton's second law. So change in momentum over time is a result of the net force, directly related. So the greater the force, the greater the change in momentum over time. If I take that one step further and I multiply t to the other side, and I have force times time, then I get that change in momentum occurs when a force acts during a period of time. So momentum changes when a force acts during a period of time. This that I just derived right here is called the impulse momentum theorem. So I'll write that at the top. Actually, I'll change this to force times time equals delta P, or change in momentum. This is, as I said, it has a official title. This relationship between force, time, and momentum, this is referred to as the impulse momentum theorem. And it simply says that any force or net force that acts during a period of time can cause the change in momentum of an object, or will cause the change in momentum of an object. In your slide, it's 6.2. It basically says exactly what I just said. So when does this take place? It takes place, as we're going to see in the next lesson or so. It takes place when a force collides with something. Now, it can be something as an object hitting the ground. So if I were to drop this pin, the pin hits the ground going pretty fast downward, but all of a sudden it comes to a complete stop. And that complete stop is caused by the normal force of the floor during that short period of time that it comes to a stop. So the momentum of that pin changes the moment it hits the ground. It's also changing as it falls, if you want to be honest about it. There is an impulse acting on the pin as it falls also. Gravitational force acts through a period of time as it falls, which would be a longer period of time than the pin hitting the ground. So really, this is, once again, as I say every day pretty much in physics, this is everyday life. When a force acts through a period of time, it changes the momentum. Putting the brakes on a car, you can put the brake, you can apply the brakes to a car in different ways. You can slam on the brakes, and it would take a great force to stop your car, but that happens during a short period of time, and therefore your change in momentum would be pretty drastic. Actually, your change in momentum would be the same, to be honest with you. Let's say you were going 30 miles per hour and you slammed on the brakes. You would come to a screeching halt, but it would take a great force over a shorter amount of time. See how those are inversely proportional? Your change in momentum, force goes up, time goes down. Or you could drag that out over a longer period of time by slowly applying the brakes. Let's say you're going 30 miles per hour and you came to a stop over a longer period of time. So if you increase the time over which the force acts, the force goes down. The change in momentum is the same either way. And let me make sure you understand that. Your final momentum is 0 when you come to a stop in that car. Your initial momentum is whatever the mass of the car times 30 miles per hour converted into meters per second is, of course. So final 0 minus initial mass times initial velocity. Your change in momentum is the same either way, whether you slam on the brakes or whether you slowly apply the brakes. It's kind of a sticky concept because when does that impulse occur, and what is causing that impulse, and more importantly, the change in momentum. This is actually the unit where we do the egg drop project. I wish we were in school. I promise you, if we get back in school, we'll do that project. But the overall idea or the emphasis of that project is this theorem right here. When does the momentum of that egg change drastically? Think about that for a second. Well, it changes when it hits the floor. Now, is the momentum of the egg going to change as it falls? Is it going to speed up as it falls due to gravity's acceleration? Is it going to be gaining velocity, therefore changing momentum? Yes. But when does it change drastically in a short period of time? The moment it makes contact with the ground. The moment that egg makes contact with the ground, it's going to be going from however many meters per second downward it's going to a complete stop. That's going to happen whether you got some structure around it or not. I mean, if I drop an egg, just a raw egg from the second floor of Brunswick High School, that egg is going to stop when it hits the floor. I promise you, it's going to stop. Splat, it's going to stop. Well, what force is causing that egg to stop? Think about that for a second. What force in the impulse momentum theorem is responsible for changing the momentum of that egg the moment it hits the ground? If you answered normal force, then that's correct. So the normal force of the ground, so if this is the egg falling, if this is the egg right here, and it hits the ground, the moment it hits the ground, the normal force of the ground, that contact force that acts perpendicular, so the little split second it hits the ground, that normal force is causing the egg to slow down to a stop. Well, the eggshell can't withstand that much force if I were just dropping an egg by itself. And of course, that force would act through a very, 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 very short period of time. Like faster than I could snap my fingers, that egg would go splat and stop. we're talking about like milliseconds probably, it would stop. Maybe not milliseconds, because the eggshell probably gives somewhat and then comes to a stop, but less than, probably hundredths of a second. So what could you do to help that egg survive? Well, you could build some type of, I call it a vehicle, some type of protective device, something to go around the egg that would help the egg survive in this collision that it makes with the ground, so that, well, what's the ultimate, what are you ultimately trying to do? You don't want the normal force of the ground to be quite as great. And what did I say about the proportion here? How are those proportional to each other? Aren't they inversely proportional? So if you could increase the time over which that collision with the ground occurs, then the force during that period of time goes down. I told you we talked about airbags. Airbags are a great example of the impulse momentum theorem. We've talked about seat belts over and over again. Seat belts are your anti-inertia belts that stop your forward inertia. If a car comes to a stop suddenly, your body, literally, not a physics body, but literally your body wants to keep going forward, but the seat belt is there in place to stop the inertia or the body in motion from staying in motion. They save lives every day of the week. I wear my seatbelt everywhere I go. But what's the purpose of the airbag? Well, you'd say the airbag is the same thing. It stops your forward motion if you're in a wreck. But what does it do? It changes the force acting on your body through this impulse momentum theorem. If you look at this side, your body is going to come to a stop in an accident, in a collision, either way. If you don't have a seatbelt on, if you don't have an airbag, your body is going to go forward and it's going to stop one way or the other. You're not going to keep going on and on and on and on forever. It's not going to be Newton's first law and a body in motion stays in motion forever. You're not going to keep flying through the air forever. You're going to come to a stop one way or the other. Seatbelts, once again, help. But what does the airbag do? Well, the airbag comes out and is a space between you and the steering wheel, or on the passenger side between you and the dashboard. And what does it do? When you hit the airbag, instead of going forward really quickly in a short period of time, it goes like this. You hit the airbag and it goes like that. So instead, once again, watch this. So instead of going forward quickly with a really big force in a short period of time, you go. So what does it do? It increases the time over which your body is slowing down very slightly. So if it increases the time over which you slow down, then it's got to decrease the net force that's causing that change in momentum of your body. So really, the change in your momentum of your body is not what's affected by the airbag. Once again, let's say your car was going 45 miles per hour, and you hit a car in front of you. You were texting like you weren't supposed to. That's why you don't text. And let's don't use you. Let's say somebody outside of you, because you don't text and drive. Let's say somebody was texting and driving, and they weren't paying attention, and they hit a car. Well, your body's going to go forward. So you went from 45 miles per hour to 0. Once again, you're going to go from 45 miles per hour to 0, whether you have an airbag, a seatbelt, or not. You're going to go from an initial velocity of 45 miles per hour with whatever your mass is, that would be your initial momentum, and you're going to come to a complete stop. Your body is one way or the other. So your change in momentum is the same whether you have an airbag, seatbelt, or nothing involved there. But if you can increase that time over which your body is coming to a stop, even slightly, then that's going to decrease the force that causes that drastically. Once again, let's put an airbag in there. So here you are here's your body coming to a complete stop, and you put an airbag in there and it goes, so something in there in between you. It's kind of like if you've ever seen the movies and you've seen stunt people jump out of a building onto the ground below, well, they're going to come to a stop if they hit the ground. I promise you. They can either jump and hit the ground by itself, splat, like an egg, or they can have those big cushiony looking airbags in which they fall into, which is what I assume they choose to jump into. And when they hit that big cushiony airbag, what does it do? It goes and stops them. They come to a complete stop over a longer period of time. They can either come to a stop really quickly, time goes down really quickly with a large force, splat, or they can go, they can increase the time over which they come to a stop, which decreases the force. That's the impulse momentum theorem. Once again, their momentum is the same either way. Their change in momentum is the same. They're going to hit the ground or hit that airbag going the same velocity. If they started from rest above, they're going to hit the airbag going the same velocity or the ground going the same velocity, either way. So that's the better way to come to a stop if you're a stuck person. So this is the impulse momentum theorem. Some easier or more common examples of impulse momentum theorem would be sports. If you catch a baseball or a softball, when does that ball come to a stop? When it hits your glove. Well, what do you, let's see, Hunter or Rachel, those of you that play baseball and softball, whatever. Raylan, sorry Raylan, I was trying to think of your name. What do you do if somebody throws a softball really hard at you? Do you just hold your glove like that and go, okay, I'll let it come to a stop, and it hits your hand real hard? No, you kind of move back with your glove slightly. Well, what does that do? It increases the time over which that ball comes to a stop, and decreases the force on your hand slightly. When does the impulse occur on when you hit a baseball or a softball? The impulse occurs the moment it makes contact with the bat and the moment it leaves. That's when the impulse occurs. So if the ball stays on the bat a short period of time, the force goes up on the ball. And that's why your composite bats and your aluminum bats imply more force to a ball, because the ball springs off of there in a short period of time. Another example would be golf. Golf, the impulse occurs when the moment the ball is on the club and the moment it leaves, it changes the momentum of a golf ball. Here's a very simple example. When you jump off of something and you land on the ground, what do you do with your knees when you land on the ground? You do this, and you bend your knees. Did anybody have to teach you to do that? I mean, did you grow up and somebody said, oh yeah, by the way, when you land on the ground, when you jump, be sure to bend your knees in the process? Well, no, you just kind of instinctively landed and bent your knees. Well, what are you doing when you bend your knees? You're increasing the time over which your body comes to a stop, and what does that do? It decreases the force of the ground acting through your legs and knees and hips to cause you to come to a stop. So those are all simple examples of the impulse momentum theorem that occur on a daily basis. Maybe not the jumping part on a daily basis, but that's what happens. Shoes, for example. I told y'all before about running shoes. I wear running shoes every day because the cushioning in a running shoe, what is it doing? It's doing the impulse momentum theorem. Every time your foot hits the ground, instead of your foot doing this with let's say a dress shoe that has a hard heel, instead of it doing this and hitting the ground with a lot of force coming back through your leg, the sole of the shoe gives a little bit every time you step or you run, and when it gives, then it's increasing the time over which your foot comes to a stop, therefore decreasing the force or absorbing the force, if that's what you want to call it. That's impulse momentum theorem, and that's what shoe companies are doing when they design running shoes to do that. They have, I'm sure they have engineers that figure out, how much force and how much displacement that material in the shoe can displace, how much weight can be withstood by the amount of force that the floor is pushing back with. So, like I said, Physics is everyday life. Physics is in everything you do. Even just walking, the simple act of walking or running there's a lot of physics involved. The next slide gives you a couple of examples of some times that are involved in an impulse action reaction. It says a golf ball hit by a driver. A golf ball is on that club head for about a millisecond. So if that time is extremely low, then the amount of net force that golf club applies to that golf ball is extremely high when you hit a golf ball. It says a baseball hit off of a tee. So if you're hitting a baseball off of a tee, the ball's on the bat for about 1.3 milliseconds. Soccer, it says a header. If you're heading a soccer ball, then it says the ball is on your head for about 2.23 milliseconds. So changing the momentum of something, it's got to require a force, and that force has to act during a period of time. Like I said, it could be a long period of time. A force can act through a long period of time. Think of a train. I used a train example in a few lessons ago. If a train comes to a stop, it's going to take an incredible force, but that force is going to have to be drug out over a longer period of time too. Trains just don't go skirt and come to a complete stop within a second or two. It has to be applied over a longer period of time. Buses, which have a lot of mass, you have to change the momentum of a bus when you come to a stop, which includes a lot of mass. Imagine if it was loaded down with students as well. Well, when that bus driver applies those brakes and applies a force to stop it, to change it, sometimes it has to be drug out over a longer period of time. So I could go on and on and on and on with the examples of impulse momentum. I'm not, and you don't have any problems to do over impulse momentum. But once again, we would be doing the egg drop project at the end of this unit. It'd be kind of a summarizing activity. I hope we get back to school, because like I said, I promise you we'll do it if we get back to school. But the impulse momentum theorem, this slide says we instinctively bend our knees when we hit the ground. I told you that airbags are designed to do that. Cars are designed with crumple zones. If you are in a high impact collision, the front end of the car is designed to crumple in. Well, what does that do? Once again, it increases the time over which your car comes to a stop, therefore decreasing the net force in the collision. So tomorrow we'll talk about conservation of momentum, very similar to conservation of energy, and we'll move on from there. We are rocking on, and we're rolling through this physics pretty quickly. And we'll have an update by next week what school's going to look like. I hope and pray that we're going to get back in school, but that all depends on if everybody stays inside and flattens that curve, like they say. We don't want the number of cases to keep going up exponentially. We want it to start leveling off, and so that we can get back to our normal lives. So I appreciate you guys listening. Keep working hard. Thanks for the emails you've sent me. I've gotten quite a few that had some answers for me, and you were rocking on. So keep rocking and rolling, and we'll see you tomorrow.